All right, let's continue our discussion of microCOS and some of its features. Again, we're going to focus on the differences between some of the operating system routines provided by microCOS and compare those to RTEMS. And actually, today we'll finish, I believe, our discussion of the operating system, microCOS. Next time we'll start looking at some of the NetBurner features, in particular uh, some of the additional routines provided in the NetBurner libraries that can be used with the microCOS operating system. Again, uh, refer to the library reference manual in the documentation directory when you're programming. But I want to talk about today queues, FIFOs, and flags. So a microCOS queue is a fixed sized FIFO. You can only pass 32-bit quantities in the queue, but of course the 32-bit quantity could be a pointer to a larger data structure. In order to use a queue, you have to allocate a queue data structure that needs to be initialized, and you also have to allocate the memory that is used to hold the messages in the queue. So here's an example where I'm creating a queue data structure. It has to be of type OS_queue, and then I'm actually setting aside storage. In this case, it's void star pointers, so it would be 32-bit pointers that we could actually stuff in here pointers to any data type. Doesn't have to be a void star. I think it could be an int array or any 32-bit quantity. I think it is recommended to use a void star pointer array, and then with 10 elements. So we can't put more than 10 elements in our queue, or we'll overflow the queue. So again, a little difference between that and RTEMS. RTEMS, we configured the operating system, and then during the configuration process, that automatically set aside space for our queue. For using the queue, you have to initialize it. So you would do this in your user main routine. So here's the queue data structure. You also have to pass it a pointer to the start of your storage, and then also the size, the number of elements that you've set aside in your array. To post an element to the queue, use OSQPost. It just takes a pointer to your queue data structure, and then the 32-bit item that you want to post. Here I'm posting a pointer to a message, but again, you could post an int or float, are all 32-bit quantities, and stuff them on the queue. And then they'll be put in, first first out order, so added on top of each other. Okay. To get an element out of the queue, use OSFlagClear. Notice it returns the element. It returns it as a void star type, so you need to cast it to the appropriate type. Here I was passing in pointers to strings, so I cast that back to char star. Again, you might cast it to an int. The arguments here are a pointer to our queue data structure, a timeout value. Again, that's normally zeros, that'll wait for forever, and then a return argument that we use to check for the error status. So we have to pass a pointer to a byte data type. FIFOs are a little bit different. They can be used to pass larger data structures, but they're really different from RTEMS queues. Whereas in RTEMS queues, RTEMS actually made a copy of the data we wanted to pass into the queue, and then actually into storage by the receiving task. microCOS FIFOs don't do that. They don't make copies. So you have to make sure that the receiving task has copied the data manually or is done processing the data before you reuse the FIFO element. Okay, the elements that are passed in a FIFO have to have a particular structure. So typically the elements are structs. The first element in the struct needs to be a void star pointer. You don't use this pointer at all. This is used by the operating system to maintain the FIFO. It maintains it as a linked list. And then after that first element in the struct, then you can have any number of data elements. Here I have a 20 element char array, but you could have then ints and floats, much more complex data structure. So the advantage of a FIFO over queue is it allows you to pass more complex data, but again, keep in mind that the data isn't actually copied like with an RTEMS queue. Like with everything else we've seen with micro-COS, you have to initialize the corresponding data structure. So here I set aside my FIFO data structure. Again, this would be a global in the global address space, because I have to access my FIFO not only in user main to initialize it, but also in the posting and pending task. OSFifoPost to actually post data structures. So here on the previous, I actually defined, I used typedef to define a new data type called myStruct. And then now I create an element of data type myStruct with this command. So my data is of that data type. So my data now has two elements in it, a void star pointer and an array of 20 character elements. So here I actually just copy a string into the char array that's part of the struct. And again, I don't do anything with the pointer that's the first element. That's maintained entirely by the micro-COS. So I post now. I can post that element. So the first argument here is the address of my FIFO data structure. And then the second is a pointer to my data, my data structure, the structure I want to pass. That has to be cast to an OSFIFO element pointer in order to keep the compiler happy. Now, this will actually post a data structure to the end of the FIFO. There's an alternate routine that will actually post to the front of the FIFO. So that means normally when you call OSFifoPend, the corresponding receive routine, you'll get the oldest item that's on the FIFO. But if you use OSFifoPost first, post an element to the beginning of the FIFO, then the pend routine would get this item off next. So same arguments, a pointer to the FIFO data structure, and then a pointer to the data element we want to put on the FIFO, and then both these actually return the status, and you should check that to make sure that there are no errors. To get an element off the FIFO, use OSFifoPend. It just takes two arguments, a pointer to the FIFO data structure, and then a timeout. Again, if the timeout is 0, we wait forever. This returns a pointer to that data structure, so we cast that to the appropriate type so that you can use it. Again, I don't get a copy of the data structure, I get a pointer to the original data structure. So I have to be a little careful about using it. If I modify the data at this point, well, in other words, rather if the posting routine modifies the data before I'm done using it here, I'll be working with the modified data. So you've got to be a little careful here to make sure that the synchronization is correct. There should be a synchronization mechanism from the routine that receives this data to make sure that the routine that's posting it waits until the receive routine is done processing the data. Okay, so micro-COS queues versus FIFOs. There are some similarities. Queues should definitely be used when passing 32-bit data items, like samples from an A to D converter. Queues do have a finite size, though. FIFOs, the underlying data structure, is a linked list, so they can be of arbitrary size. FIFOs can be used to pass larger data structures. So can queues if you use pointers to the data structures. Again, queues are a fixed size. Normally messages are added to the end of a queue or a FIFO, but there's a special routine available to put a message to the front of a FIFO. Note the message is not copied when working with a FIFO, so again, I think I've warned you about that a couple times. Okay, another element we have in MicroCOS is we have flags. These are similar to RTEMS events, but with RTEMS events were local to each task. Each task had its own event register. In MicroCOS, flags are global. So in the flag routines, you have to pass a pointer to a corresponding flag structure. You didn't have to do that in RTEMS. So to initialize a flag, you call OSFlagCreate. Again, this would be done in user main typically, and my flag here would be a global data element. To set a flag bit, it's easy. They're 32 bits long, so the easiest way to do that is actually use a hexadecimal value. This is going to set the high bit and the lowest byte, and the high bit and the most significant byte of the 32-bit flag data structure. And then you have two routines, just like we had with RTEMS, to wait on flag bits to be set. We can wait on all of them to be set, and here we need to indicate via this hexadecimal value what bits we're actually waiting on. We're waiting on the bits with a corresponding 1 in this particular data value. Since F is in hexadecimal corresponds to 1111, so all ones in the lowest nibble of the least significant byte here, and then here this would be the 4 bits, the 4 most significant bits in the second byte. So here we're waiting on 8 different bits to be set, and we're waiting on all of them to be set, and we'll block until that condition is true. Or, alternatively, you can wait on any one of a number of different bits to be set. And then A here is decimal 10, so that would be 8 and 2. So this is, the second and fourth bit out of a nibble, out of all nibbles. So we're waiting on any one of the odd bits out of the 32 bits available to be set. Okay. You use OSFlagClear to clear the flags in a flag object, and then you can check the state without actually waiting on a particular bit to be set using OSFlagState. Okay. I think that's all the new routines that I wanted to talk about. I think this is coverage of everything you need for the next project. I do have here an example using FIFOs. This is posted on the website. An example using MicroCOS FIFOs. It also uses a semaphore for synchronization. But here I create, again, a FIFO data element called myFIFO-L that has, again, this voice start pointer at the first element of the structure, and then I'm passing a message back and forth. So I'm also using a semaphore. Let me scroll down to the bottom here to user main, where I'm creating 2 tasks with different priorities. Here's where I initialize my semaphore, and I initialize the FIFO. Okay, so actually let me pause there. So we have to initialize those in user main. Notice I'm initializing the semaphore to 0 because it's going to be used for synchronization. Okay. Here in task 1, it prints a message, and then it actually copies a string using SIPrintf, count equal, count's going to increment from 0, and then every time through the loop here, count will increment by 1. So this is going to copy the message count equals 0, then count equal 1 into here. I've created a struct of this myFIFO element type. So it's going to copy this message into the char array that's in this local data element. Okay, and I don't do anything with the pointer element here. So I've copied the message in, and then now I just copy that element onto my FIFO. Okay, so that's all I do here. Now, before I go back around and change the message, I'm going to wait on a semaphore that's going to be released on the receiving task, the task that actually reads the FIFO, so that I don't overwrite that message. Okay, so actually, I put a delay in here of 2 seconds. Otherwise, these messages are just printed out too quickly. But I'm using both the FIFO and then waiting on the semaphore, so they're both being used as synchronization mechanisms. But I'm also using the FIFO to pass data. So in the receive routine, so the first thing it's going to do is wait for data in the FIFO. So it will block at this point until it gets that message across. Now what I do here, and this is the safe thing to do, I copy the message out of this FIFO element that I got here. I got a pointer to that element in the other task. So I copy the message into my own private message buffer using a string n copy. Okay, so I copy that into my own private message. Now I can immediately post the semaphore, allowing the posting task to immediately modify the FIFO data element with no concern about the data being corrupted. Okay, I don't have any delay here. The only delay is actually in the task. But so I've posted it, letting the other routine know that I've got a copy of the message. Now I could do some sort of data processing. In this example code, I actually just print out the message. Okay, so I think this kind of covers everything you need for the next project. So we can talk about it we're going to meet via a Zoom meeting today, and so we can talk more about the project then.